Hi there, and welcome to another Pencast for the course Reasoning and Logic. This one is about functional completeness. Now, as you may have read in the book, we say that an operator or a set of operators is called functionally complete when we can express every formula in propositional logic using only this set of operators. So for this exercise, imagine we have a new operator. It shouldn't be called an operand. My apologies for the wrong name in the video. But we have a new operator and we'll call it star, as in P star Q. Now what does this operand look like? Well, if we make a truth table, this is the truth table of our operand. 0, 1, 0, 0. And my claim is that this operand, together with the negation, is functionally complete. So the set containing the negation and the star is functionally complete. Now, how can I prove that? Well, the first idea you might have is to show that the 16 different truth tables that we can have for a binary operator can all be created using only the negation and the star. Yes, that is one way to prove it. However, you've already done something else if you've done the exercises in the book. One of the exercises asks you to prove that the set of negation, or, and, implication and by implication is also functionally complete. With this new insight, all we now need to show is that with our negation and star, we can create the negation and, or, implication and by implication. In fact, for one of the homework exercises, you have shown that just the negation and the implication are sufficient to create all other formulas. So you could even just leave it at those two. But for this video, we'll show you how you can create all 5 of them. So how do we do that? Well, let's start with the most simple one. We have to create not P. Well, since we're allowed to use the negation, not P is already done. Not P only contains negations and stars. And let's take a look at what we get when we negate our star operator. Let's look at the truth table of that. So not P star Q is 1, 0, 1, 1. Now I don't know about you, but that reminds me of an implication. The implication Q implies P, because that has exactly the same truth table. So apparently, P implies Q can be written as not Q star P, as demonstrated by our truth table above. Okay, so that's the implication done. What about the disjunction? Well, we know that P or Q is not P implies Q. In other words, that must be not Q star not P. And what about and then? Well, P and Q is the same as not P or not Q. Thank you, De Morgan. Negated. So not P or not Q. What does that become? Well, for that, we can just use the rule that we just discovered for the disjunction. So it becomes not Q star not P. In other words, not Q star P. And finally, let's take a look at the by implication. Well, the by implication is there 2 implications, and we know how to do both implications and the conjunction now. So let's fill in the implications first. P implies Q was not Q star P, and, well, the other way around. And now we just need to use the and. So we get, yeah, a pretty messy, but hopefully you agree, correct claim, or equivalence rather. A way to write P if and only if Q using only stars and negations. And there you have it, our proof that the set of star and negation can create all other operations. In other words, it is functionally complete. And with that, I'll see you in the next video.